Hi there, Turgeon here, bringing you physics from afar. We have a situation. We have an exit ticket from class that involves a bouncing ball, this time off a wall. I think the example given originally was off of a floor. And the trick here is think in terms of components and understand how impulse and momentum relate. So the first thing we got to do is figure out what is this 50-degree angle, and the emphasis is on with the wall. So the 50-degree angle is with the wall, which is vertical, so it's with the vertical. Draw a vertical line that matches this hypotenuse, this main vector. Now we've got a 50-degree angle between those. I immediately think that this part looks like a cosine situation, and the perpendicular part is a sine situation. So if you do sine of 50, I can get this 3.83 off of this velocity of 5. Now, why did I want the 3.83? That's because I'm interested in the horizontal, because it's the part that's perpendicular to the wall that actually changed. Think about that for a second. It's the part that came away from the wall that is going to change. So I have a velocity going toward the wall, and then I have a velocity going away from the wall. The wall imparted a force to the left. The change was to the left. So I originally have 3.83 going toward the wall. I have 3.83 going away from the wall. Let's think about that. That is a total change in velocity. Oh, wait a second. Why do we even want the change in velocity? Because I want to find the change in momentum. The easiest way, we have delta P, which is change in momentum, is equal to mass times change in velocity. So my instinct is to get that change in velocity. And that change in velocity is negative 4.596. Sorry, change in momentum. Because the change in velocity was negative 7.66. Because if you think about it, if you go from $3.83 to owing $3.83, you must have lost $7.66. That's a negative here. It's kind of like soft and faded. So I have my change in momentum of negative 4.596 kilogram meters per second. Not kilograms times meters per second. Kilogram meters per second. Oh, my impulse is the same thing. Impulse is the change in momentum, negative 4.6 Newton seconds. Second question. We've got these original vectors which were going in this upward direction. And the PDF scanner kind of like blotted these out. That's interesting. This first one was pretty long. Now I'm wondering if, yeah, I mean, I see the original paper over there. But anyway, this first vector was pretty long. So my answer to this first question is this diagonal vector that looks fuzzy and red going up and to the right. If this was the change, then I can add the change. The impulse is the change. So there's this additional momentum being pumped into the system. There's this additional impulse that's delivered to the current momentum. So it's this plus this, which means now it's got a momentum up and to the right. This original one had this momentum starting here. Hope you can see my cursor on the video, and going up. So we added this extra momentum to that. So the total goes like so. This next one had this momentum pointing downward like so. So when we added that momentum, it was this, which actually took away, this impulse takes away some of the vertical momentum, but adds some horizontal momentum. So it's essentially a vector sum where we're drawing the resultant. So to recap, theme here, momentum is a vector. So we can do all the things we did with other vectors. We should break it into components. And the other theme is that impulse is the same kind of quantity as momentum. It's kind of like work is the same kind of quantity as energy. Kind of like weight is the same kind of quantity as normal force. So therefore, I can add onto this momentum by contributing an impulse. Let's look at the next exit ticket. The other exit ticket is an inelastic collision. I think I got the names mixed up. This one should be called inelastic collision. Go figure. So we have a wad of clay moving to the right. We like wads of clay because they stick to stuff. Sticks to a stationary ball. What are we going to do? This comes after the inelastic collision video. Before I get into changing kinetic energy, before I even write down kinetic energy equations, I think instinctively collision. Let me write out the momentum equation. mv plus mv equals mv plus mv. That's supposed to be a star. This is like the master equation for momentum. mv plus mv equals mv plus mv. There's usually two moving objects and two moving objects to consider. Now we can simplify that just like the energy master equation. My original velocity is 4 times 5, but I'm going to call it mass of 4 and velocity of positive 5 because we're going to consider the right to be the positive direction, plus 0. That thing is at rest, so it's got a momentum of 0. And that's equal to the total mass times the final velocity. Now wait a second. You have this other mv. Yeah, but at the end when they stick together, I like to consider that one object. I like to consider that one object at the end. So object in the beginning, stationary object, one single object at the end with a mass of 10. Plug in the numbers, you get 2 meters per second for the final velocity, which, by the way, is the final velocity of everything in the system. So that's the final velocity of the center of mass of that system, which, by the way, means that before this collision even happened, even though there were two separate objects, that was the velocity of the center of mass of those two separate objects. Now, I can find my kinetic energies. Kinetic energy in the beginning was just the kinetic energy from the clay, 1/2 mv squared, that's 50 joules. Kinetic energy at the end was the kinetic energy of this like dual object, so 1/2 times 10 times 2 squared. Now, if you forgot to combine them in the kinetic energy part, because you got to remember, usually don't, it's kind of a no-no for separate objects, don't combine the masses. Just calculate each kinetic energy individually and add them up. It's a scalar, so it's just no negatives to worry about. In this case, you can add the masses because it really is one object. That's only a kinetic energy of 20 joules, which is interesting. Yeah, it actually lost some mechanical energy here, probably went into vibrations and heat and sound. Collisions often make noise. We had a change in kinetic energy of 30 joules. We want to call it negative 30 joules, indicating it is a loss. You can say 30 joules lost. You can say 30 joules dissipated. You can say 30 joules less, but you want to indicate the loss with a negative or some word. Impulse on the large ball, or just the ball, because it's larger, it's 6 kilograms. If I do force times time m delta v, I got to think about that. I don't have any indication of force and time to get the impulse, so I got to look at momentum. If I look at the momentum, I take the mass times the change in velocity. Well, the large ball started from rest and then was moving at 2. So the change in velocity of the large ball was 2. Just think, what did the large ball do? That's 12 Newton seconds to the right. If the teacher asks you for a direction, you got to indicate a direction. Otherwise, that can be pretty casual. Now I'm giving information. I'm given information about time. I'm asked about the force. So force and time, that's impulse. I already know the impulse is 12. Don't know the force. Time was a mere 0.2 seconds. That's a force of 60 newtons. Again, to summarize, this time less about the impulse momentum relationship, even though we did that. This is more about the new master equation, a new conservation law, conservation of momentum. mv plus mv equals mv plus mv. Does not mean conservation of kinetic energy, though. That's so interesting. It actually lost kinetic energy. We can relate every force interaction back to impulse momentum. We did change the momentum. It did require an impulse. And we can relate that impulse to force and time, which is how it's defined. This has been Turchin bringing you physics from afar.